This paper explores the benefits of representing and processing semantic knowledge extracted into graphs within the emerging paradigm of semantic communications. It introduces a novel end-to-end pragmatic optimization semantic communications framework, optimizing the transmitter, the latent space representation and compression, and the receiver. The proposed architecture leverages the cascade of large language models, LLMs, and graph neural networks, GNNs, as semantic encoders, where information to be shared is selected to be meaningful at the receiver given the locally available knowledge. The system model is composed of essential blocks: a semantic encoder, a wireless channel, and a semantic decoder. The semantic encoder associates the input knowledge graph with an array of low-dimensional embeddings, each containing semantic information about a node, the nodes connected to it, and the relations connecting them. Two semantic encoders are proposed: enclum, GNN, and enclum, FFN. Enclum, GNN cascades a pre-trained LLM module with a GNN module that processes the combined output from the LLM module with the inherent graphs topologies of the data. Enclum, FFN consists of a LLM followed by a feed-forward neural network, FFN, bottleneck, aiming to compress the initial feature vector associated by the LLM to each node, without considering the associative relationships in the knowledge graph. The proposed approach is numerically illustrated to enhance both compression rates and communication robustness. The paper also discusses the potential of achieving high compression rates in communication by incorporating relations that link elements within graph embeddings. It proposes sending semantic symbols solely equivalent to node embeddings through the wireless channel and inferring the complete knowledge graph at the receiver. This research paper proposes an end-to-end graph-based semantic communication system, where a large language model, LLM, is utilized to associate initial features with node descriptors, followed by a feed-forward network, FFN, that compresses node representations via a bottleneck layer. The channel encoder modulates the compressed vectors into complex symbols, which are then demodulated by the channel decoder to recover the latent space vectors. The semantic decoder infers the knowledge graph from the received message by classifying nodes and relations using multilayer perceptron, MLP, and transformer encoder architectures, respectively. The system's performance is evaluated using mutual information estimation and cross-entropy loss minimization. The loss function combines a cross-entropy term with a weighted mutual information component, reflecting the interdependence between variables across the semantic channel. The system is trained using a dual objective optimization strategy that combines cross-entropy loss minimization with mutual information maximization. Numerical results demonstrate the effectiveness of the proposed system. The node classification accuracy exceeds 98% for an embedding compression factor of 24 or smaller, with the graph neural network, GNN, based encoder outperforming the FFN-based encoder. The F1 score metric, measuring the equivalence of nodes and relations between transmitted and decoded knowledge graphs, shows that the proposed encoders outperform traditional techniques in the low signal-to-noise ratio, SNR, regime, requiring about 14 dBs less SNR to reach their maximum F1 score. The average compression gain factor for the semantic approaches is 5.54 compared to Huffman encoding and 7.17 compared to 6-bit encoding. The proposed system's ability to capture graph topology information and condense semantics of graph nodes enables effective knowledge graph representation learning and compression. The proposed framework for semantic encoding and decoding of knowledge graphs demonstrates effectiveness in optimizing compression of knowledge representation. Two variants for semantic encoding, enclum, GNN and enclum, FFN, are introduced, with enclum, GNN exploiting the relational spectrum of nodes and enclum, FFN treating each node isolated without considering its neighborhood. Numerical results validate the effectiveness of the proposed framework, achieving 99.5% and 94% node classification accuracy for enclum, GNN and enclum, FFN, respectively. Enclum, GNN also enables a compression up to a factor of 24 for the node's embedding size, while maintaining node classification accuracy almost independent from the compressed embedding size. The inclusion of graph topology information in enclum, GNN and the superior efficacy of GNNs in condensing the semantics of graph nodes contribute to these results. The proposed graph-based semantic encoding and decoding functions outperform traditional Huffman and 6-bits coding in the low-average SNR regime, requiring about 14 dBs less of SNR to reach their maximum F1 score in simulation settings. These enhancements in compression rates and communication robustness are realized through the proposed design. The references cited provide a comprehensive overview of the current state of research in semantic communication, knowledge graphs, and graph neural networks. Works by Merluzzi et al. And Calvanese Strinati et al. discuss the vision for 6G networks and the importance of semantic and goal-oriented communications. Other references, such as those by Countouris and Pappas, and Gundas et al., explore the concept of semantics-empowered communication and the need for context, semantics, and task-oriented communications. The proposed framework builds upon these concepts, leveraging graph neural networks and knowledge graphs to optimize compression of knowledge representation. The results demonstrate the effectiveness of the proposed approach, highlighting the potential for enhancements in compression rates and communication robustness. Future work may focus on exploring the applications of this framework in real-world scenarios and further optimizing the performance of the proposed approach.